everybody doing today? Are you able to hear me? Yeah. Okay. I haven't. I see a lot of familiar faces. How many of you come to the meetups we have very often? Lift your hand. Okay. Great. Yeah, welcome. And how many of you have used these products, right? 40 gig. Lift of hands. Okay, very good. What's the latest firmware you are having? Anybody? Okay. So you might have read the data sheet, right? Like it is 1,500 page or something like that. So we have given 45 minutes. So we are going to speak fast, listen fast, and then we will go from there. So we are going to tick tack here. So I will take the first. Okay, where do I see? Okay, here are the files. Okay. So if you see the block diagram here, right, this captures the big picture. The virtualization point of view, couple of bullets, right? Server virtualization, we all know even from the previous generation, VMDQ for emulated path and SRAOV for direct assignment. And then in this one, network virtualization is what is given more emphasis. So things like VXLAN, NVGRE, in my mind, I just visualize them as more like a zip code, right? You don't need to look at all the 5 tuple, but have a zip code type of a quick lookup, and that's what the right tag based, right? That's what we do in the network virtualization support in 40 gig part. Now flexible. The reason why I asked what firmware version you are having is to communicate the flexibility of the part, right? There are examples which we can go over where even after the product was released, there are standards evolving, and we were able to upgrade the firmware and then cater to the requirement of the customer. So that is very exciting in this time, right? And we have flow director with intelligent load balancer, and then other exciting things are more like virtual bridging support, WEPA and other things. So to have the control and management for both host side and switch side. So that's the big picture, and so I'm going to give the floor to Helen, who is from R&D, as was told, right? So go ahead and then talk about the internals, and I'll come back.
Yeah, this is a black diagram from a data sheet. Everybody can see that from online. But I will not go through all the details of the NIC itself. I just want to introduce something different comparing to previous version of Intel NICs. The bottom block is the actual silicon architecture. The up one is the logic block on the host memory. In the bottom, we have the PHY and the mic. It can support 2 by 40 gig ports and at most 4 by 10 gig. We have 4 versions of NICs with different speed of the ports. And up there, this internal switch for TS and IS packet buffers. On the up layer, there's a line engine who is responsible for the TS and IS packet passing or even modify some offload fields. So you can see that there's IS schedule and IS fields there, which can tell the engine to do some offload, to do some filtering, to classify the received packet to different queues, different VSIs, or even more. From the TS side, there's also a TS schedule. Can do a lot of things. The typical thing is to do something for QoS. In the top of the silicon architecture, there's the physic function of PF and VF modules inside the NIC. The NIC will talk to software driver with co-working with the host memory listed on top of the silicon architecture. The bandwidth are pretty high, as is use a PCI Gen 3, at most 8 lane. So the bandwidth is quite high compared to previous generation of NICs. In host memory, just a lot of memory will be reserved and be used by silicon. So you can see that this PF objects, VF objects. Basically, the host objects could be TSSQ objects and admin queue objects and FCOE ISTS objects, which typically don't support FCOE actually. So this is the typical silicon architecture and the whole logic architecture of the I40, that means XL710 or X710. But I'm not a hardware guy, so that's it. I have listed some key differences comparing to 82599. All guys knows 82599 very well, but comparing to XL710, some key changes I think you guys may be very interested in is that we have supported 3 hash mechanism on X710. The traditional one is top-based algorithm, and we have added one more simple XOR, and the symmetric simple XOR could be quite useful for those proxy products or something like that. These 2 algorithms are new on I40 hardware. And for the hash input set, this is quite important, but I'm not sure if everybody knows that, as has just been enabled recently. Why is it important? Because the field we can select for hash calculation. Previously, we have no choice to do that, but now we can select the field from at most 128 bytes from the packet. We can select maybe one or more of field for hash calculation. This is quite flexible for most of field or hash scenarios. Actually, the input set is the same idea on flow director. For flow director, we can still select what type of field, maybe one or more from the 128 bytes from packet to do hashing or to do flow director. This is quite important. And another important thing that for the ISS side, we have a concept of flow type, or call that the PC type. The definition is a bit different from the same one on 82599, because, for example, for IP, for the flow type of IP on X710, which doesn't include UDP, doesn't include TCP, doesn't include HTTP. The definition is a little bit different from the hardware side. So we need to care about that during the implementation. For the flexi payload side, on the last generation, the previous generation of NIC, just only 2 bytes can be used for flexi byte. But on X17 we have up to 8 bytes to do that. This is a big change. Definitely there's a mask that can be used for that. For the flow director, there's always more resources, but the big things change is we just use exact match only on X17. That's a big change. I know there's quite a lot of other changes, but I think this piece could be something key. We always have more VSR resources, Q resources, or other resources comparing to previous generation of Intel NICs. This is a NIC anatomy. It's just to introduce what happened inside the NIC. It's just the IS path, because IS path is maybe it's more complicated. We can see that the packet can be received inside the NIC and stored on the packet buffer, and it will do the QoS management in the left side, the left block, and then do some parser. Parser means that we can tell the packet types. What's the packet types of the parser of the packet received? X17 can support more than 150 packet types, which can be recognized by the hardware. In previous generation, we don't have too many packet types. After that, there's a classifier switch and classifier post-port filters, which is used to do some old the classification clusters, including ISS flow director and MAC filter and possibly others. Old filters is a little bit like a pipeline, but there's action there. After the classification or filtering, the action could be directed packet to a specified queue or specified VSI, or just drop the packet. So a lot of action defined inside the silicon. The last step is to do some packet modifier to maybe just to remove the CRC bytes we have already offloaded to us descriptor. That's a packet modifier. I think this is inside, the logic is inside the silicon. Maybe we don't care about too much. Classification is a big thing on the NIC. Hash filter can distribute the received packets to the queues you allocated to this specific VSI, and as I said a moment ago, the field used for hash calculation can be selected. We have a feature named configuring input set, which is used for selecting the field for hash calculation. And for flow director is actually it's Intel flow director, which can pin the flow of packets to a specific queue, some other destination. The flex payload byte is larger than previous generation of NIC, and the flow director can run in pass-through mode. The flow director can extract the data from and to the IS descriptor, and then let the IS logic to distribute the packets to which queues. Tunnel support is totally new on X710. We have supported quite several typical tunneling types, but the number is still ongoing, incrementing. After the firmware update, we can support more, but maybe we don't support all The latest example is that maybe we will support MPLS. That's a new requirement. So cloud filters can do checksum flow and flow classification on X17 NIC. There's quite a lot of other changes, but maybe I don't need to mention too much, as everybody knows that quite well. So previous piece are the key changes. Maybe it's quite useful for you guys.
Sorry, I have a question. For the flow director. Oh yeah, sorry. For the flow director, you said that we can ping flow to the specific queue. Can we, go to the CPU queue? Go to CPU, or it's go to the that queue is go to CPU, is right?
The queue is the NIC queue.
I know, but it's that queue can be go to the CPU or not?
The queue finally will go in the host memory.
Go to host
which can
memory.
be read by the CPU.
Okay,
Yeah.
thank you.
So the flow director, right? You're pinning flows to queues, but is it using the RSS hash over here?
Different, but you can use both.
Well, RSS you won't get symmetrical, right? In the forward and reverse directions for a flow.
Flow director is using an exact match to do packet matching. RSS is using hash.
Okay.
Symmetrical RSS on RSS. Yeah, we can.
So you have a version of RSS that is symmetrical?
We have a feature named, we need to configure the hash function or algorithm. We have a feature. We can select which type of RSS hash algorithm to do that RSS.
Okay.
Yeah.
Thank you.
Thanks.
One more question about the flow
Sure.
director. Does the 8 bytes, can that also be any 8 bytes in the packet, or are they sequential?
Sorry?
The 8 bytes associated with the receive classification for the flow director.
Yes, it's a feature named flexible payload, which we can select up to 8 bytes in the payload, not just a header. The payload to do flow director.
Any 8 bytes.
Sorry?
Is it
And-
contiguous 8 bytes?
Yeah,
Up to 8 bytes. You can.
No, do they have to be together?
yeah.
No, we can have a
Okay.
mask there to select which, maybe even bits. What type of bits you can.
So you have the mask for that, right?
Yeah.
Mask.
Sure.
So in the third point over there, how do you use RSS after FD? Like FD itself will choose a queue, right? Or is it a set of queues?
Sorry, how to use RSS?
RSS after queue, like after using FD in the pass-through mode?
After what?
So you said,
The third one says the FD can run in pass-through mode, right? So he's saying after FD, how do you use the RSS?
like, is it
Together.
a set of queues for FD flow director or one queue?
RSS can distribute the packet to different queues.
So flow director will choose a queue first.
Flow director in the pass-through mode is just extract the data, do nothing about the classification. The classification is done by the RSS. This is the pass-through mode, but without this mode, you still can use flow director to distribute the packet to different destinations in, for example, queues.
Okay.
Yeah.
Quick question. So, I'm here. So, for the two function blocks, which one work first and which one work later?
You mean flow director and RSS, right?
Yes. So, if one packet come in, right? It will match.
I think based on the sentence should be flow director first, and then let the RSS to distribute the packets.
Then no conflict. So the flow FD said that okay, I need to send to Q1. And
But
then-
here, FD is just used to extract the data
Okay.
to the RS descriptor. After that, RSS will is responsible for packet distribution.
Okay, got it.
Yeah,
Thanks.
thanks.
Is there any
So the
plan to
internal
increase
switch
the...
that you showed in the block diagram, right?
Sorry, block diagram?
The internal switch that you showed.
Yes.
So that is for packets that switch between the VFs.
Which one?
Oh yeah, the internal switch.
It's not. It could be VF, but it's, in the concept is to switch the packet between different. Maybe VSI. VSI is a concept on X17.
So if there are two VMs that are running on top of two different VFs, and if there's a packet between that is going between these two interfaces.
Two different PFs, you mean?
Two different VFs.
There's no way to do that. All the VF switch is on top of on single PF. Otherwise, you need to add the mechanism to do that.
But I can pass on one of the VF to the guest as an SRIOV interface, right?
Yes, you mean the two different VFs on two different VFs. That's not the case.
No.
Two different VFs can be switched on a single PF.
Yeah, I'm talking about two VFs which are belonging to a single PF.
Yeah.
And the traffic between these two VFs go through this internal switch, right?
Yeah, can be switched.
So is there a performance constraint on the internal switch? Like what is the rate that it can handle?
Yes, the performance could be a little bit challenging as the bandwidth and the internal processing capability will be shared by all the VFs.
Right, because like I could have 128 VFs, right? Because there are 128 RX and TX queues, so
the performance could drop a little bit if you use more VFs to do VF forwarding or switching.
Okay, and the internal switch is also available in the 82599 EB as well, right? So it's
which one?
The previous NIC.
No, there's a different structures design.
Oh, okay.
It's different. It's totally different.
So the 82599 doesn't have this internal switch.
Something called L2 switch is there.
Okay.
It covers also virtual functions, right?
Right.
That is just pure L2 switch, right?
Okay.
Yeah.
So the other question that I had was, the NCAP that you support, right? The cloud overlay.
NCAP, DCAP. Right.
Yeah. So
no,
instead of GRE and NVGRE, can I have MPLS?
Hardware doesn't support NCAP, DCAP for now.
Yeah, but you do support the other overlay protocols, right? Like the NVGRE and the GRE VXLAN.
Yes. So but there's no NCAP, DCAP there. Just checksum and a packet distribution.
Yeah, you don't do an NCAP, but you do classification based upon that.
Yeah, hardware doesn't support that.
Yeah, so do you have plans of supporting MPLS or such kind of?
It could be quite soon, as asked by quite a lot of users.
So why don't we hold the questions on specifics, right? I think we have a lot more information to cover.
Okay.
And we are going to be standing out there.
You can ask me questions later. If
go direct to me. If maybe time is quite a little bit tight, I can go direct to you too, please.
Okay, thank you.
So MJ, a quick question here.
Okay, quick question. Okay.
I'm sitting on this side.
Where? Here?
Here.
Okay.
So is there any plan to increase the PCI bandwidth from by 8 to maybe by 16 or something and get like full 80 gig?
With this generation, we have by 8, yeah.
Okay.
With this, yeah.
All right. And are there any limitation on using the the splitter that splits the 40 gig into 4 10 gig ports?
We do have, right? We do have 40 gig part, and then we do have 4 10 gig part variations. We call both of them 710 family.
Okay, so you could potentially get an 8 10 gig ports using that splitter.
Correct.
Okay, and no particular limitations on that, right?
No.
Okay, all right, thanks.
Okay, so I think I have 10 minutes or 20 minutes. We have 2 sessions. One is more into functionalities, another is more into performance. How many of you are interested in performance first and functionalities least? Okay, how about functionality first, performance least? Okay, very good. 50-50. Okay, I see Kevin, Stephen, a lot of people, familiar faces. Okay, so I'm going to quickly go through functionality quickly because I see a lot of people. Some people are building appliances, some people are building cloud infrastructure. So to set the base, I'm just going to quickly go through, what is the requirement from top to bottom, right? I think you saw from bottom to top, and we are just going to see top to bottom quickly, and then we will get into the performance, right? Okay, where are we? So many of you definitely is aware of this model, right? Like the traditional 3-tier data center networks. What are the scaling problems you see here? Anybody can shout it out, please? What are the scaling problems? Right? If you are going through 3 layers, right? When you go through multiple layers, your congestion and all those things is very difficult to control. And then you're talking about packet drops and all those things. Now, when we're talking about cost reduction and we're talking about having both storage and networking traffic, that's a problem, right? And then with the latest applications spawning a lot of east-west traffic because of many reasons, right? You have multiple VMs, but the very model of the application itself, web server application itself, is now spawning multiple servers needing to service the request. Now with variance in latency and this type of structure, you are not going to be catering, right? So those are the driving factors for the 2-tier flatter network, right? So quickly, if you see here, that's what we talked about, right? Aggregate switches, run out of ports, needing to use large switches and routers. And then the frame header was getting processed at the core switch router. And then when all the traffic goes through that, and you have to do a lot of processing, L3 forward processing there, then it is going to be also become a bottleneck and introduce congestion, right? And then again, the 3-tier cloud network was not designed with latency in mind by default. So that is the biggest problem for the east-west traffic and then service model. And then again, with the multi-cores ramping in performance, the top-of-rack switch cannot keep up with the both storage and network bandwidth, right? So these are the things. And then again, cost, we all know. Now that gets into the 40 gig infrastructure going into the blades, right? So that takes your 40 gig getting down, and then next layer, maybe 100 gig getting into the core switch. Now you see only 2 layer, you don't have 3 layer. Now you have a better control of congestion control, and thereby you are able to cater to having convergence in traffic. That reduces, that puts everything on Ethernet. You don't need to have a separate fiber channel or things like that. And if you see here the small block diagram here, the tunneling can be done at multiple locations. If you have time, we will look at what are the trade-off people do in the tunneling locations, and we'll go from there, right? So again, 40 gig advantages, that's what happens. It's latency and design from the beginning, and then you don't need to carry all the, BGP and all the other TCP IP offloading features. You can eliminate them, and you can do the core switching instead of doing it routing, right? So if you see here, right, as we just talked about, tunneling at vSwitch, tunneling at NIC, tunneling at top-of-rack switch, there are various choices. Now, if you do it at near to the VM, then you are able to know the endpoint. So that makes sense to do it at vSwitch. But then you are taking CPU cycles, which is good for Intel, and which is good for you because it's flexible, right? vSwitch. Now, what if somebody is not using hypervisor based, and if they are using NIC, SRIO, and things like that, then you cannot use vSwitch based tunneling. So you need to go at NIC based tunneling, right? Or even if you use vSwitch based tunneling, but let's say you have your TCP segmentation offload that's being done in the NIC, and the NIC doesn't support your tunneling protocol. Now you will be ending up disabling that feature in the NIC. The moment you disable that, you are already using CPU resources for tunneling. Now your offloadings are not working. Now you are going to do more and more processing with the CPU, which is good, but you need more CPU for that, right? So now that's where the 40 gig what we are talking about shines, because you can, with a firmware update, you can support tunneling protocols coming, and then you don't need to disable your offload when you are introducing your tunneling at the vSwitch level, right? Whereas if your NIC is not firmware based, it is just designed at the silicon, and then your new protocols come, then you have to be disabling, and you will not be able to do that at the vSwitch. So that takes the possibility to go to the NIC. When you do it at the NIC, again, if you are using SRAOV, then you need to come there, right, to the NIC, because we are not at all using hypervisor-based tunneling. So you are doing it NIC and the SRAOV. Now, the way the NIC design partisans the offload and SRAOV modularly and keep it one after another, you will be able to possibly do some of that at the NIC, right? And then the last thing is, the last choice is top of rack, doing a top of rack switch. Now, the thing is, if you look at the top of rack switch, it's more like a tunneling tagging, right? But if you are moving the tunneling itself there, you need to identify the endpoint. The endpoints can be identified if you do it at vSwitch very easily. The VMs can be identified. But now you are doing the tunneling at a top of rack switch, which means now you need to do the deep packet lookup to find out the VM's identification, right? So only choice is if the endpoints, all of them are residing in the same rack, then possibly you don't need to do even to the tunneling. You can just use the L2 itself, L2 forwarding itself, and thereby you can optimize some of the table size what you are using. So these are the possible locations. I'm already getting 10 minutes notification here. Okay. Again, when we said we use the where it is, we use the vSwitch, right? When we say we use a vSwitch, and then you are the switch, the real hardware switch. The vSwitch may be still evolving, and some additional functionalities may need to be still implemented. From that point of view, there's a delta in your feature list compared to what is there in the NIC and what is there in vSwitch. So if you want to treat all the traffic equally, then you may want to send, that's where the WEPA comes in, right? You want to send everything to the NIC, right? Even though if it is within the same rack or if it is out of the rack, you want to send it, thereby you get the same treatment. But the only thing is, if you see the spanning protocol, for example, that may not let the NIC do that hairpinning within the same rack. So then you need to do improvement or firmware update for that, right? How many of you are also realizing the spanning protocol which was designed previously is not at all going to be useful anymore, or it is going to be limit the network utilization? Because we are talking about virtualization, we are talking about taking the juice out of the infrastructure. Now you have a spanning protocol and you are not able to use the network infrastructure effectively. So there are a lot of new standards coming. But again, this is just an example of how WEPA is used. And on the right side, you are seeing how WEPA is implemented in our 10 gig. So this is the packet flow as how VXLAN uses and how we have that. Okay, I was planning to do for 5 minutes. But I think in the choice of time, I'm going to stop here for functionality point of view. I'm going to quickly go to the performance point of view. MDGRE, step-by-step walkthrough for performance, right? So you want to see some of these things. So performance comes into two flavors, right? What is the measuring performance measuring yards? One is throughput, another is latency, right? So if I talk about it, you are going to see me, oh, the guy from Intel is talking about the NIC. What else we are going to hear? So I'm going to take a paper and pen. I'm going to give 2 credibility resources for you. You want to write it down, okay? Tonight, before going to bed, tonight, go and Google this. MIT fast path, MIT fast pass, FASTPASS, right? That is the credibility of latency. They use DPDK and they are saying, if DPDK is so fast, I should be able to dream about a network with 0 queues, right? And that's what they did it. And that talks about latency, right? So you can, there's a white paper, a fantastic white paper, you want to go and read it. Now, the moment I say that, some of the bulb may go saying like, oh, if that's the case, then possibly you are trading off throughput for latency. So what do you do for throughput, right? So again, write it down. CMU, I think you heard cuckoo hash. Look at that. That is a white paper which talks about how DPDK and cuckoo hash algorithm together gives the best throughput. Now, if the 2 academic institutes can achieve that, why can't you achieve it? You can achieve definitely the performance, right? So think about that, and latency, possibly you can hide it. What are the techniques that are available in DPDK for hiding latency? Anybody can throw some words? How do you hide latency in DPDK? Parallel processing, okay? Anything else? What do we do in DPDK for hiding latency?
I guess the buffers are pre-mapped, right?
Using caching. Okay. Huge page support. TLB shoot down. AVX. I think you all know more than me in DPDK. Okay, great. So the way I remember is this one. Okay, I am a more visual person. So let's say there's a dinosaur, right? The dinosaur neck is pretty long, and it takes water to go from the mouth to the tummy, maybe 30 minutes. So that's a latency of the memory, right? 70 nanosecond latency. Now, the dinosaur doesn't want to go thirsty, right? You don't want your code to be waiting, right? So what do? What do you tell the dinosaur? 30 minutes before you become thirsty, why don't you go and start drinking the water? Thereby, by 30 minutes, you will have the water in your tummy, you will not be hungry, right? We have a concept called prefetch. So the memory latency you know, why not you plan ahead? If this is the instruction you want your data, why don't you plan ahead 70 nanosecond and then give a heads up to the memory controller, hey, I may need this data. The reason it is heads up is you are telling the memory it's a heads up, so do not delay any data dependency. If there is a data dependent instruction, keep going ahead because it's a heads up. So the memory will go and fetch it. By the time you come to your real need, the data is standing there. So your cache is there, but if the locality is not even there, you can do that, right? So from today, whenever you see any dinosaur movie, you remember latency hiding techniques, right? What about throughput? What about throughput? What do you do for improving throughput? Any ideas? What does DPDK do? Don't do much. Okay. So there is a variation, right? So this is like this, right? You have CPU and you have NIC, and they have the cache line for communicating, and there is a throughput limiting factor, right? Which is the penalty of going there and getting it. So let's say I have a bunch of acorn here, and all I am given is a squirrel to pick up the acorn. So then the squirrel is going for each packet and then taking it up and coming back. So the walking over the bus for the cache is the latency, and for each packet if you do, you are incurring the penalty and throughput is not going to be much. But what if you are given additional tool, not only a squirrel, but also a, what is this? And this is a bulk API, right? We have something called bulk API. So use the bulk API, thereby what you are doing is you are not going for each packet, but whenever you are going and taking a whole truckload of packets. Now you have amortized that overhead across multiple packets, right? So now you got your throughput, you got your latency improved, and that's the way to go, right? So go and search, write this down, RTE_prefetch. Go and put it in Google. It will not go to any Linux, it will go to DPDK very fast, right? How much time I have? 5, okay. So beyond that, right, this is code, right? In hardware, what do you do? So okay, I now know that, okay, I can do this, I can do that in software, but in hardware, what do I do? That's what I think we have quickly. So if you see the memory, right, the memory, you are plugging in the memory, go and look at whether all the memory slots are really populated. There are Linux tools available. I have a white paper which talks about it, so you have my email, you can send it. I can send that white paper to you. But the point is, without even opening the platform, you can find out how many of your memory slots are populated. Why that is important? Because in the DPDK command, you can give a parameter to tell use this many memory channels. Why that is important? Because what we are doing is somebody was telling parallel processing. We are really using parallelly all the memory channels to put the header across. Thereby, when the CPU takes the bulk, when you are talking about do the bulk, what bulk is good if the hardware is not prepared for it, right? You may go and say, get me that many, but then you populate only one memory slot. Then you are going to go one by one, right? So populate all, and then communicate to the DPDK that this many is populated. That's why we have this minus n. Minus n indicates number of channels. If you don't communicate that minus n, then it will assume there is only one. Again, you are going to create a bottleneck. So understand your platform, fully populate the hardware, and tell the DPDK that I have populated this many, and now you will see the performance improvement, right? Okay, that is one. And then somebody was talking about how huge page, TLB, yeah. So I don't want to go into the details, but yeah, definitely these are important. In fact, I think I will say that if you put the order of performance things, I think the first thing should be the huge page. Where the NIC should be plugged in. And again, somebody was asking, are you planning to go for the next generation NIC? Now, this is Gen 3. Now, in your system, you want to understand the topology, where the PCI NIC, some PCI slots may be directly connected to the highest efficient pins that are coming from CPU, something may be least efficient. Sometimes you may even, if it is an old generation processor or platform, it may be even coming from a south bridge, not directly coming from that. So you need to understand that. You need to ask for the block diagram and then make sure you are plugging in the highest performance slot, right? That's what you're talking about. And then NUMA consideration, which talks about if you have multiple slots, then in your score mask, whatever CPU number you are saying, just make sure that that is the local, right? Now, how many people logically think somebody using a 2-socket system, the numbering will be CPU 0, CPU 1, CPU 2, CPU 3, all are closer, and then this may be CPU 45, 46. But the firmware can number the CPU, ACPI tables can number the CPU any way they want. It can be 0, and the hyperthread sibling need not be 1. Hyperthread sibling may be 9. And in your mind, if you think 0 and 1 are neighbors, they may be far away, right? So you want to first know in any platform what is the L-core numbering, draw that in a paper and then pin it. Because tomorrow somebody else will work on the project, he will put 0, 1, and the performance will not be good, right? So did I make sense there? The CPU numbering, L-core numbering? Okay. And then firmware, right? Since we're talking about a NIC which is based on firmware, keep a closer look. There's a link there. Always update it. BIOS setting. See, the CPU, the by default, I'm repeating, by default, the manufacturer may have programmed the platform for lowest power option, which means they may be putting it in sleep, and we are now wanting to send packet at the highest performance, so you want to remove all the power settings such that it is highest performance, but not for lowest power, right? So again, BIOS settings, and then the big train, you see one engine, but sometimes it's a bigger train. You may see 2 engines pulling that single train. I have not seen 4 engines, but more than 1 engine is needed to pull the load. What I mean by that is 10 gig you might have done with 1 CPU, but with 40 gig, if you want to get almost what you want to get, then you want to go for 2 CPUs, which means in the command line you need to tell I'm using 2 core, not 1 core, right? So whatever you did for Niantic, just don't blindly do it. Understand the command line and do it. I think my time is up. Any other questions? Not now. We can talk about it later. Thank you. Nice talking to you.